a hypothesis for the splattering salsa that you have you say is proof of God, Jack, but nah, science always wins, you see. Yes, my answer to that question is the conservation momentum. Okay. Here is your salsa bowl. Okay. Your salsa bowl is made up of the mass of the jar and the mass of the salsa. Okay. And all of that entire system has a velocity in the negative j direction because it's a vector, so we're going down, and this is the floor here. Okay, so it's got a velocity times by the sum of the total mass, and that's equal to its momentum, p. Okay, and you can see here m, which is the big one here, is the sum of lots of small masses, because the salsa is obviously made up of little bits, made of like bits of pepper, and obviously because it's a liquid, you can break it apart and it can fly off in little droplets, for example. So this entire system has this much momentum. Okay. Now the next part is the impact when it hits the floor. Now all that momentum is conserved between the two points, between before it hits the floor and after it hits the floor. So the momentum is always conserved between those 2 points in a perfect system. It's not a completely perfect system. Some energy, for example, some momentum is lost to the floor, or some energy is lost to the floor, or whatever. But there's enough is conserved in order to have the effect in which we saw in the video. Now, when the salsa hits the floor, okay, because the salsa is essentially it's very viscous sort of thing. It's going to break apart. Droplets are going to go everywhere. Large blobs are going to land on the floor. That sort of thing. And if we take the mass of the parts which are flying off, for example, a big blob of salsa which falls out is going to, when it hits the floor, its momentum, because it's got very large mass, when it gets conserved, it's going to have so much velocity. It's only going to fall a small distance, and that's evidently what we see in the video, is a very large blob of salsa falling a very small distance, typically just outside where the impact point was. Some blobs will be smaller, and so because they have a smaller mass, they've got to have a higher velocity in order to conserve momentum. Okay, as you can see from this, if you just imagine there's one m in here, if I lower the m, I've got to increase the v in order to keep it balanced. So a smaller mass in this system would constitute a higher velocity. So smaller blobs will travel further because they have a higher velocity. So that means that very, very small blobs will go absolutely flying, and that's why they can reach the wall. That's sort of summed up here. Okay, so total mass. So all the momentum's conserved between the before and after. So here is the after. It's hit the floor. A big blob has come out that's got so much mass, and it's got a very small velocity. It lands just outside. We've got slightly smaller ones here with a slightly higher velocity, so they fall further away, okay, from the impact point. And finally, you've got very small droplets which have very high velocity, which will hit the wall here, okay. And that's sort of summed up here as well. So there you go. It's science, it's science, Jack, not God. Sorry to rain on your parade, but you're asked for this. I'm sorry. Toodaloo.